Hello everyone, welcome back to our YouTube channel. In today's discussion, we discuss a very interesting question from the real analysis, and this question is asked in the ISI MSc Mathematics Entrance Exam 2025. In this question, what is given? F is a mapping from the real number set to the real number set, and it is a continuous function. Okay, it is given in the question, and this continuous function satisfies this integral inequality for every a less than b and every c less than d. Here a, b and c, d are arbitrary. Okay, then we have to prove that f is a constant function. Okay, we will prove it by the method of contradiction. Initially we will assume that f is not a constant, then we will get a contradiction, and this contradiction implies that f is, will be a constant function. Okay, so f is a mapping from R to R is a continuous function given, and it satisfies this inequality is also given for every a, b, c, d which satisfy a less than b and c less than d. Okay, so we will name it equation 1. Our claim is to prove that f is a constant function. Okay, so we will go by the method of contradiction. So we will assume that f is not a constant function. Okay, f is not a constant function means what? We will get two real numbers z1 and z2 such that f of z1 is not equal to f of z2. Okay, then we will consider a is equal to z1, b is equal to z1 plus epsilon, c is equal to z2, and d is equal to z2 plus epsilon, where epsilon is greater than, strictly greater than 0, is a positive real number. Okay, then we will plug these a, b, c, d values in equation 1. Then we will get this thing, this inequality, because b minus a is nothing but epsilon, and d minus c is also epsilon, so it gives epsilon minus epsilon. Okay, I hope that up to this point everything is clear. And this quantity is nothing but 0, but we know that this quantity is also greater than equal to 0. We are getting here this quantity is less than equal to 0, but since it is a modulus thing, so it is also greater than equal to 0. Therefore it implies that this quantity itself is 0. Okay, then we will divide epsilon on the both sides, then we will get this equality. After that we will take the limit epsilon tends to 0 on the both sides, and we know that modulus is a continuous function, so the limit comes inside. Okay, and we know that the limit of the difference is the difference of the limits. By using the algebra of the limits, we will get this equality, equation 3. Okay, now here we will apply a very celebrated result of the Lebesgue point. Lebesgue point means what? Every Lebesgue point, this is the definition of a Lebesgue point. If a is a Lebesgue point of the function f, then it should satisfy this limit equality, and its generalized can be written like this, in the generalized form, limit a epsilon, any ball, a epsilon f of x dx, and divided by the measure of the ball, b a epsilon. Okay, measure of the ball, and this limit converges to f of a when epsilon goes to 0. This is the definition of Lebesgue point. If a is a Lebesgue point of the function f, then it should satisfy this limit. Here measure means the volume. Okay, but in this limit form, it is a particular case of the Lebesgue point. In this here our ball is nothing but the interval a to a plus epsilon. Okay, and its measure is equal to what? Length. Length means it is equal to epsilon, because a plus epsilon minus a gives the epsilon, so its measure is epsilon. So here we are integrating over this set and we are dividing its measure, and if a is a Lebesgue point, then it should satisfy this limit. And we know that if f is a continuous function, then every point a belongs to R is a Lebesgue point. So in our case it is already given that f is a continuous function, so therefore every real number is a Lebesgue point of the continuous function f. And if you want a concrete proof how every point of the continuous function is Lebesgue point, then you can check the description box where I have attached a video link, and you can find the proof that every point A belongs to R is a Lebesgue point if f is a continuous function. So we are recalling that result here. Okay. Since our f is a continuous function, so every point is a Lebesgue point, means every point A satisfies this limit epsilon tends to 0 1 by epsilon integration from a to a plus epsilon f of x dx is nothing but f of a. Okay. So for the time being, believe me that this result is true, and you can check the description box for a concrete proof. Okay. Now we will use this equation 4 in 3. Then we will get what? This limit is nothing but f of z1, and this limit will be f of z2 by using equation 4. Okay. So we will get f of z1 minus f of z2, and right hand side is equal to 0. So it gives 0, and this implies that f of z1 is equal to f of z2. But it is a contradiction to the equation 2, because in equation 2 we have assumed that f of z1 is not equal to f of z2, but we are getting the opposite thing, means f of z1 is equal to f of z2. So it is a contradiction, and we are getting this contradiction due to our assumption that f is a non-constant function. So this implies that our assumption is wrong, means f is a constant function. Okay. So I hope that you all understood this proof. Thank you all. Bye bye.